Module 1, Fundamentals of Metallurgy. 1. Introduction to Metallurgy. Welcome to the first module of our course on metallurgy. In this module, we're going to explore the foundational principles of metallurgy, the science and technology of metals. Metallurgy is not just about studying metals, it's about understanding their properties, behaviors, how they can be extracted from their ores, how they can be processed, and how they can be modified to meet specific needs. Metals are everywhere, in the structures we build, the tools we use, the vehicles we travel in, the devices we hold in our hands. Without metallurgy, modern civilization simply wouldn't be possible. From ancient blacksmithing to cutting-edge aerospace engineering, metallurgy has been a constant companion to human progress. Definition: metallurgy can be defined as the science and technology concerned with the properties of metals, their production, and purification. It involves studying the physical and chemical behavior of metallic elements and their mixtures, known as alloys. Importance of metallurgy. Engineering design: selecting the right material for a job requires knowing how metals behave under different conditions. Manufacturing processes: from forging to casting to machining, metallurgy informs the methods used to shape and treat metals. Performance and safety: correct metallurgical practices ensure that metals perform as intended, resisting wear, fatigue, or corrosion. Branches of metallurgy. Metallurgy is often divided into several subfields. Physical metallurgy, concerned with the structure of metals and how that structure relates to their properties. Mechanical metallurgy deals with the behavior of metals under mechanical forces, including elasticity, plasticity, and fracture. Extractive metallurgy involves the extraction of metals from their ores and refining them into usable form. Powder metallurgy, producing components from powdered metals through compaction and sintering. 2. Historical development of metallurgy. Metallurgy has roots that stretch back thousands of years. Archaeological evidence suggests that humans began working with native metals like gold and copper as early as 6000 BC. These were soft metals that could be shaped with simple tools. The Bronze Age began when humans learned to alloy copper with tin, producing bronze, a harder and more durable material. This period marked a major leap in technology and weaponry. The Iron Age saw the widespread use of iron and steel, allowing for even stronger tools and structures. In more recent centuries, the Industrial Revolution transformed metallurgy from a craft into a science, leading to the modern understanding of atomic structures, phase diagrams, and alloy design. 3. Classification of metals and alloys. To effectively study metallurgy, we first need to categorize metals. Ferrous metals contain iron as their main component. Examples: pure iron, steel, cast iron. Known for their magnetic properties and strength. Commonly used in construction, transportation, and manufacturing. Non-ferrous metals do not contain significant amounts of iron. Examples: aluminum, copper, zinc, titanium. Typically more resistant to corrosion, lighter, and non-magnetic. Important for electrical wiring, aerospace, and packaging. Alloys. Alloys are mixtures of two or more elements, where at least one is a metal. Substitutional alloys: atoms of the solute replace atoms of the solvent in the crystal lattice, e.g., brass, copper and zinc. Interstitial alloys: smaller atoms fit into the spaces, interstices, between metal atoms, e.g., steel, carbon in iron. Alloys are made to improve properties like strength, corrosion resistance, and ductility. 4. Structure of metals. Metals have a crystalline structure, meaning atoms are arranged in repeating patterns. The arrangement of these atoms determines many of the metal's properties. Common crystal structures. Body-centered cubic, BCC. Example: alpha iron, chromium, tungsten. Generally harder and less ductile. Face-centered cubic, FCC. Example: aluminum, copper, gamma iron. More ductile and easily deformed. Hexagonal close-packed, HCP. Example: magnesium, titanium, zinc. High strength but limited ductility. Grains and grain boundaries. When metals solidify, they form grains, small crystals that grow until they meet. The borders where grains meet are called grain boundaries. Smaller grain size usually leads to greater strength, Hall-Petch relationship. Grain boundaries can influence corrosion resistance and ductility. 5. Solidification and crystallization processes. When molten metal cools, atoms arrange themselves into a crystal lattice. The rate of cooling affects the grain size. Slow cooling, larger grains, more ductility. Rapid cooling, smaller grains, higher strength but less ductility. Impurities and alloying elements can influence the crystallization process, leading to different microstructures and mechanical properties. 6. Phase diagrams and alloy systems. Phase diagrams are maps showing the phases present in a material at different temperatures and compositions. Binary phase diagrams. These involve two components. They are essential for understanding alloy systems and predicting microstructures. Key features. Eutectic point, the lowest temperature at which a mixture of specific composition will melt. Paretectic and monotectic reactions, special transformations between solid and liquid phases. The lever rule allows calculation of the proportion of phases at a given composition and temperature. 7. Mechanical properties of metals. Metals are chosen for applications based on mechanical performance. Key properties. Strength, resistance to deformation or breaking under load. Hardness, resistance to indentation or scratching. Ductility, ability to be drawn into wires. Toughness, energy absorption before fracture. Fatigue resistance, ability to withstand repeated loading. Creep resistance, resistance to slow deformation under constant load at high temperature. 8. Testing of metals. Understanding these properties requires standardized testing methods. Tensor test, measures strength and ductility by pulling a sample until it breaks. Hardness test, Brinell, Rockwell, Vickers methods measure indentation resistance. Impact test, Charpy and Iser test measure toughness. Fatigue testing, cyclic loading until failure. Non-destructive testing, NDT include ultrasonic testing, X-ray inspection, and magnetic particle testing, allowing inspection without damaging the part. 9. Heat treatment of metals. Heat treatment is the controlled heating and cooling of metals to alter their properties. Common processes. Annealing, softens metal, improves ductility, and relieves internal stresses. Normalizing, refines grain size and improves toughness. Quenching, rapid cooling to increase hardness, often followed by tempering. Tempering, reduces brittleness from quenching while retaining hardness. Case hardening, hardens the surface while keeping the core tough. Heat treatment is crucial in tailoring metals for specific applications. That concludes Module 1. Here we've established the core principles, from the historical background and classification to the structure, properties, and treatment of metals. This sets the stage for Module 2, where we'll focus on applied and advanced metallurgy, extraction processes, corrosion, welding, and modern metallurgical innovations.